In this video, we'll go over a quick overview of how to graph polynomials and rational functions. Now keep in mind for this class, we don't need to know all the details on how to graph them by hand, just enough to be able to recognize that it's a graph of a polynomial, let's say, or a rational function. And then you can compare with graphing calculator or online utility. So let's get started with polynomials first. So here is a general example of a polynomial. Starts with a degree n. Notice how the subscripts basically mean that these are coefficients of the term with a degree. And a0 corresponds to the constant term, then you have the x term, and all the way up to degree n. So the degree of a polynomial for us would be the highest exponent, and the leading coefficient is the coefficient of that term with the highest exponent. So a few characteristics to know about graphing in general is that the degree of the polynomial and leading coefficient, we'll call it a instead of an, just not to keep it a little less confusing from previous section. And end behavior, so that helps us, especially if we know the end behavior and we have several graphs to choose from, for example, or we can look at graphing calculator. But I like to characterize the degree for even versus odd. And even, the most common even degree polynomial is y equals x squared. Notice how I drew a little parabola. So that's the easiest one to remember. So if the leading coefficient, we'll call it a for the ax squared. Notice how the both ends are facing up. Now notice we don't know what's happening in the middle. So you can have actually quite a few things going up and down. But we do know that both ends go to positive infinity. Why is that? Because whether it's a negative number or positive number, if you square it or raise it to an even degree, fourth and so on, then both ends are actually going to go to positive infinity. And same idea, if n degree is even, but the leading coefficient is negative, then both ends are going down because now you have the negative that makes them go to negative infinity. And similar idea, if degree is odd, I think of y equals x cubed, probably the most basic odd degree function. So same idea, one end is going down. This is the left end or the negative end as I like to think of it, because think of -1 cubed, let's say, you're going to get a negative number. So the bigger negative numbers are, you're going to go to negative infinity. And on positive end, you're still going to go to positive infinity. And the situation is reversed if the leading coefficient is negative. So instead of memorizing, try to make up some cases for yourself just to kind of keep track of. Something else that is nice to know, y-intercept is relatively easy to find on your homework. You'll find it a very good strategy to be able to graph polynomials. That's as usual. If x is 0, then you're probably going to get a constant term as your y-intercept. X-intercept is y equals 0, set equation equal to 0, then solve. This tends to be much more difficult, and this part we're going to just gloss over a little bit, because depending on the degree, it may be very difficult to find zeros. But this is still a good idea to keep in mind on. Maximum number of turning points. Turning points, so let me kind of quickly draw a little bit. Let me get my tablet. So let's say if we're trying to draw turning points, the turning points we're talking about are maximum and minimum. It's these 2 points. And there is a limit to up to how many you can have. Now, look with y equals x cubed. We don't have to have any turning points. But it turns out that you can have up to 1 less than the degree turning points. For example, degree 3, the maximum number of turning points it can have is 2. So you cannot have more than 2. Again, it's maximum and minimum. Notice how the function stops increasing and starts decreasing. That's why they're called turning points. So yeah, so degree 3 cannot have 5 turning points, for example. If you have 5 turning points, chances are you have a degree 6 polynomial, depending on end behavior, or 7, so you can also tell by other characteristics. Then let's keep going down. Again, sometimes you can identify the polynomial by looking at end behavior and y-intercept. I threw in a few examples from the book, which I will show you how to access the book in my math lab. It's actually fairly easy once you figure out where everything is. So I threw a few information, just a little bit. For example, you have x cubed. This is a degree 3 polynomial. End behavior is as above. The left end is going down, the right end is going up. The y-intercept is -9, the constant term. So we identify the graph to be D if you find that section. I put the page number. It's from the book that's in my math lab. If you have a physical book, depending on edition, might be different, but you can still find it. And so on. I threw in a degree 4 polynomial, but with a negative leading coefficient. And same kind of idea. And the end behavior, both ends were going down. The y-intercept was 0, +15, and we identified the only answer it could have been was G. So again, for your homework, you'll either be given choices to choose from, or you can graph it on your graphing calculator and just kind of compare, and that way you know. For rational functions, what if you have a division of two polynomials, p of x over q of x? We need to know something. Defining characteristics of rational functions are asymptotes. This is very important to know because even if you graph rational functions with a calculator, it's not going to show you asymptotes, and you have something else there too, which is called a hole, which sometimes arises too. Holes are not shown either, so you do have to know to supply that information for yourself. Okay, let me scroll down a little bit. Vertical asymptotes are a little bit easier to understand because it's basically you can never divide by 0 in the denominator. So what's happening when the 0 is denominator, you get like this vertical boundary that you cannot cross. Now x can get close to, for example, in the first example, to -2. And you're going to get very large numbers because think about 2 in the numerator dividing by a very small number, extremely small, because if it's really close to -2, you're going to get very small number denominator, very close to 0. It's going to blow up, so the function is going to go to infinity or -infinity. So the most important characteristic is that your function is reduced. We're going to see one example where it's not. Here in number 1, it is reduced. Notice you cannot cancel the 2 in the numerator with a 2 in denominator because you cannot factor it. X plus 2 is like a unit. The factors have to be multiplied by one another in order to cancel. So for example, if you'll see x plus 2 over x plus 2, then you can cancel. And the x plus 2 is not going to give asymptote in that case. You do give, if you can cancel, you do get a hole in the graph of a function. We're going to see one example later. But in this case, in number 1, you cannot cancel, so the vertical asymptote is x equals -2. It's what makes it 0. Okay. Another example, f of x is equal to x plus 1 over x minus 4. Again, vertical asymptote is x equals 4. It's important to put x equals to and not just a number because it's a vertical line, and vertical lines have equations x equals to a number. Here is one example where it's not canceled. X plus 2 over x squared minus 4. Notice how I factored denominator and I canceled x plus 2 in denominator and numerator. So we end up with 1 over, should have been x minus 2. There are some minor typos sometimes. So then the remaining denominator, I'm going to put 2. So this is going to be +2. Okay, so the vertical asymptote would be x equals 2 because x plus 2 is actually gone. Okay. So note x equals 2. X equals to -2. I really need to fix this. Excuse me. The factor that was reduced forms a hole on the graph of the original function. Horizontal asymptotes are a little bit more difficult to understand, but the idea is what is happening to the function as x gets very large, goes to infinity, or goes to -infinity, very large from negative end. So what happens to y as x increases in either direction. And for now, we're going to discuss 3 possible cases. Later with the limits, we're going to see, well, they're still the same 3 cases, but we're going to understand them a little bit better, I believe. What if you have degree of the top less than the degree of the bottom? So what's happening there is that the denominator is going to take over. It's going to get very large. And because denominator is large, the whole function is going to die off essentially, or go down to 0. And so that's why it gets to be y equals 0. Again, I try to make up quick examples like y equals to 1 over, say, x plus 1. Okay. Notice how the degree of the top, a constant, is degree is 0 usually, and the degree of the bottom is 1. So the bottom's larger. So imagine x to be, say, 5 billion. Then you're dividing 1 by 5 billion, you're going to get a very small number. That's why it's going to be y equals 0. Now notice in case 2, the degrees match exactly, so the function does not die off. But what do you get? You get a y to be a number, which is specifically leading coefficient of the top divided by leading coefficient of the bottom. So let's take a look at that example. Notice how it's going to be the leading terms that are going to be very important, because when x is huge, -5 and -4 are not going to play a big role. And even if you had an x term, it's not going to play a big role. But it's 2x squared divided by 3x squared. Notice how you essentially are going to end up with 2/3, because x squareds will cancel. So it's going to be y equals 2/3. Now the last case, a degree of the top is greater than the degree of the bottom. You don't have a horizontal asymptote in this case, but you may have something else. We call it oblique, y equals some x plus b, if the degree of the top is exactly 1 larger than the degree of the bottom. We can find it by long division, which I may do an example later. But for now, let's try to graph by finding vertical and horizontal asymptotes and x and y intercepts. So here we actually will graph, but you can still check with your graphing calculator. Let's start with the one I mentioned earlier, -4 over x plus 2. The vertical asymptote is x equals -2. What do you think horizontal asymptote will be? It's y equals 0. All right. Y-intercept, I plugged in x equals 0, so we get -2 for the y. So it's 0, -2. X-intercept, you set the equation equal to 0. Note how you can multiply both sides by denominator, but then we're going to get -4 equals 0, which doesn't make sense, so there are no x-intercepts. And notice the graph. I actually pulled this graph from a graphing calculator called Desmos online, and notice how I drew the asymptotes on top of the graph. So originally there were no asymptotes, but I drew them, and I also supplied the y-intercept because we had it at 0, -2. So I actually marked it on the graph. So this is what it looks like. We could also figure out, once you plot the point, we know the graph is going to follow the asymptotes. It has to go down here, because if it's going to go up, it's going to cross x-axis, and it does not cross x-axis. There are no more x-intercepts. So you can kind of figure out where it goes. On the left side, to the left of the asymptote, you would have to plot a point to figure out if the graph is above x-axis or below x-axis. You could pick -5, for example, and notice how it's going to be positive. Or you can, again, check with your graphing calculator, as long as you know. The next one I did was x plus 1 over x minus 4. I'm going to speed up a little bit. I don't want this video to be too long, but I'll let you look at the information, maybe try to graph it yourself, but this is what the graph looks like. We found a couple of points, y and x intercepts. Again, I drew the asymptotes myself on top of this graph, and I noticed because of these 2 points, I could figure out that this graph was here, and this graph to the right of the asymptote had to be above, because if it was below, it would cross x-axis, and I don't think there were any more additional points. Okay, so real quick now, for the last one, we could factor the top. So notice x plus 4 is gone, so there were no asymptotes really. It's a line of y equals x plus 3, but there is a hole at x equals -4. And notice how I drew the graph. I actually drew it by hand. It's y equals x plus 3. This is the graph. But notice I put a hole at x equals -4. And if you draw it on a calculator, it's not going to show up. So you have to put it in yourself. And that's it for this video.